Professor Giorgio Parisi. He's a renowned theoretical physicist, currently a professor of quantum theory at the University of Rome. In 2021, he won the Nobel Prize for his groundbreaking contributions to the theory of complex systems. What secrets lie in the elegant movement of a flock of starlings? What can complex systems tell us about the nature of life, our universe, and ourselves? Welcome, everybody, to an exciting episode of the Into the Impossible podcast. We're joined today by an inspiring physicist, a man who's made many contributions to our understanding of nature and especially the understanding of what are called complex systems. And we're going to get into that. But the first thing we love to do on this podcast, Giorgio, is to talk about the title of the book that you have written. It's called In a Flight of Starlings, The Wonders of Complex Systems. Can you explain, Giorgio, what does the title mean and what is the cover art? What does it illustrate on the cover picture?
The point is the following. I've been interested for a long time in the flight of starlings. Starlings are very interesting birds, and they are doing the flight in a very huge group of thousand, especially in the evening, just at the moment when they have to go to sleep. And the point was that the image that these birds are doing are really amazing, fascinating, but no one knew exactly how they could communicate to do this movement. And the thing that was most fundamental, no one really knew which was the form of the flock. Because when you see a flock of birds, you see the image that you have on your retina, but you don't see the three-dimensional shape. And usually, in order to see the three-dimensional shape, you use two eyes. But with two eyes, you can see the distance of objects which are nearby. So which was the solution? The solution was to put two eyes. We decided to do an experiment about that. It took a few years to do, and people are still working on the problem, and to see how really the starling flight, and the solution was to put two eyes at a distance of 20 meters. Of course, you cannot put really your eyes at a distance of 20 meters, but you can put some camera at a distance of 20 meters, synchronize the pictures, photograms of the starling with these two cameras, and having a three-dimensional reconstruction. This is not so easy, but at the end we succeeded to do. So when we decided to write a book on complex systems, one of the chapters was certainly dedicated to the birds. After the book was finished, we decided with the editor, the author, we discussed the chapters. We discussed to put the chapter on birds, on starling in the first, and also because it is in some senses the one that is most fascinating, most easy to be understood. And at the end, we started to discuss the title, and we arrived to that one.
Yeah, it's a brilliant book. It's very short, it's very readable, and it's endorsed by none other than our friend Carlo Rovelli, who is coming back on the podcast for his 20th book, I think it must be, on white holes. And I take you guys, I don't know if you know this, but Carlo and I recorded the first ever audiobook by Galileo. So here is Galileo. There's a mini puppet of Galileo. He's holding his telescope. And it reminds me in your book, when you talk about devising not maybe a new way to see things that were never seen before, but a different perspective. And Galileo said the following, when he was inducted into the Linnaean Society?
Linnaean, yes. Of the lynx of the animal.
That's right. He said, a scientist should measure what is measurable and make measurable what is not yet so. Was this discovery that you made with your colleagues, was this hiding in plain sight? Was this something that could have been discovered earlier, or did it really require the new technology not maybe of the telescope, but of the camera technology. Could your discoveries have been made 30 years ago, 40 years ago?
The things on Starling, I think that was just the first moment it could be done. The reason is the following. We needed to have a huge number of photographs because it was really a movie. And in order to do this before us, you have to do, we estimated that we needed anyhow, and we used tens of thousands of photographs. Now, and now this have to be used in somewhat in a digital way because they have to be analyzed by computer. Now, the very idea to have something like an archive with 10,000, maybe 100,000 photographs, and look into them, digitize all of them is something that really a big mess. So I think that we started just at the moment with the camera technology was good for using these things. Because we had at that moment, there were 4 megapixel camera. There was the upper professional one of Canon that were able to shoot 8 photograms per second. So that was just the one that went out. The price was $5,000. We had to buy 6 of them or 8 of them. So, but it was not a real problem of the price. The point is that the things really did not exist, digital camera of high precision and high speed.
When I look at your history of collaboration, it's impossible for me to not ask you about your advisor, Nicola Cabibbo. Can you talk a little bit about him as an advisor? And maybe explain a little bit for my audience, what was he known for? What was his big contribution to physics that probably warranted a Nobel Prize, in my opinion? But what was Nicola like as an advisor, and what did he do for physics?
Nicola, it was a wonderful advisor. He was a wonderful advisor because, first of all, he was very friendly with the student. And the things that he really did, he was transmitting enthusiasm for the science. Was transmitting interest in doing science in the good way, in the right way, and without caring too much of the publicity of the result. But the real point was to understand deeply what one have to do. And also the other things that I remember very well of him, that when we were discussing some possible things to study together, the point was that one should try to pick something which is amusing. I think that it's amusing for the scientists, and I think that this is important because if you start some project which is very boring, at the middle you are going to stop it, you are not going to finish it. So to have some kind of amusing, amusement, which is the same kind of amusement that may have people when they solve a puzzle. But it's important to have amusement. Now, Nicola had been a really great scientist. In the 60s and the 70s, he made a lot of discoveries about the behavior in which what people call radioactivity. People nowadays call weak interactions. How some forces which is not strong as the strong forces, and the thing that he really understood the way that these particles interacts. We'll say at the present moment how quarks do interact in the weak, and introduces what people called after him the Cabibbo angle. And the Cabibbo angle is at the basis of present theories of weak interaction. He could have had the Nobel Prize in 2008, I believe, but things happened. The Nobel Committee decided to not give to him, doing some argument which I think were factually wrong, but sometimes also the Nobel Committee makes some mistakes.
when I think of him as an advisor and a contributor, it didn't seem like he was bitter about not winning. I mean, it seemed like he was committed to his students and to the science with enthusiasm. So is that a trait that you mimic with your students? Did you learn as an advisor to many students, and formally and informally as well, to many millions of people probably? What lessons in terms of education or being a mentor did you learn from him?
Yes, I mean, I think that I'm trying to transmit enthusiasm for science, and enthusiasm for science is quite important to do, and of course, you have to do it the right way. I mean, so you have to sit down near your student to understand what they're doing, have them to do, and also you have to encourage them. I mean, if they are able to solve things in some way, which is not the best way, I think that you should let them go on and not explain that could be done in a much simpler way, because otherwise you take out from them the joy of having discovered something. And I think that I've done things well, because there was a Nature, the magazine Nature made a prize for mentoring, and this was, I think, in 2015. There was the prize for mentoring in Italy, and I think I was one of the 3 guys that won the prize for best mentoring in Italy. So, and this was based also on the reports of my student, who wrote a very enthusiastic report.
Well, certainly so. I think it's Latin, and you'll correct me if I'm wrong, but the word educate in Latin is educare, and it means not to pour into, but to bring out of. And so I think you've brought out a lot in your students and your colleagues, and it seems to me you have quite a good deal of humility, as well as sort of the confidence to pursue these incredible questions. And when I was reading the book, I started to wonder about these murmurations. So a murmuration is a collective noun for starlings when they flock together, and it almost as if they become a different entity, like a different organism. Can you describe what they're actually doing? Why do they do this? Is it to scare off predators? Is it to migrate? Is it to attract mates? What is the evolutionary purpose of a murmuration?
Well, that was well understood by biologists much before we entered in the game. The thing is clear. These birds do not like cold weather. Therefore, in summertime, they stay in North Europe. I mean, and during the winter, they arrive more or less in November to Rome, and they spend the winter up to March. In that period, things they have to find a place which are relatively warm, because they do not have many things to eat. They have some fat, but the amount of fat that they are able to burn is not so high. So the point is to find a place which is good, which is warm, that you must have some trees which have leaves, and there should be not too many cats that go on the trees, because that would be better for other reasons. So what happens is that when they come, they go in the countryside during the day. So they're commuting. They go in the countryside in the day, and they come in the evening to sleep inside the city. But anyhow, they commute, and when they come back, they have to find out a good place. Some of them will find out the good place, or maybe the same as the previous day, so they start to make some kind of murmuration movement on the top of the place, and the other bird that arrives, they see this kind of murmuration, and after they becoming bigger, and when it's the moment to go to sleep, which is usually half an hour after the dawn, they go to sleep, And this murmuration can be seen from a very large distance. I remember that I was able to see murmuration on the sky in Rome more or less at 10 kilometers of distance. So they are something that you can easily see in the sky, because you don't see usually the sky objects that moves, make change, and so on.
Yeah, they're quite mesmerizing. Are they describing them with the tools of condensed matter physics? Do they exhibit phase transitions? Do they exhibit, first order or free energy? Are there things that we can connect to our, introductory thermodynamics classes that a student can understand about their behavior? Or is it really unique to these birds and the fact that they're birds? Are there commonalities, critical points, phase transitions? How do they behave from a physicist's perspective?
Well, from the point of view of physics perspective, one has to take care that these birds are out of equilibrium, because usually when one is doing the standard textbook for thermodynamics or on, one is looking to a system which are at equilibrium, and now at what people call thermal equilibrium, and now these birds are not at thermal equilibrium, but however, thermodynamics, the physics of these last years have done a lot of progress to discuss a system which are not at what people call thermal equilibrium. And therefore, one can use in describing these birds by physical law. One can write something like a equation motion, collective equation motion. One can speak of a normalization group, phase transition, and the things that happens, that the way that these birds move is essential that they stay essentially at the critical point. The reason for which they choose the type of parameter which they use in doing in flight to say near the critical point is that when you are near a critical point, near a phase transition, the speed of information inside the system is going to move very, very fast. Indeed, what happens in this case, because in half a second, all the flocks have the size to turn in one direction and another direction. We know that when they turn, the few birds that start to turn, other, which is typically in the center of the flock, other birds are following, but the signal that someone is starting to move propagates very, very fast.
My thumb is very busy right now holding up good old Albert, but if yours is free, please go ahead and hit that like button. And don't forget to subscribe. It really helps us with the algorithm.
And when I thought about the murmurations, it crossed my mind that maybe human beings can exhibit these same kinds of behaviors but not know about it. Are there phenomena, maybe not physical phenomena, because we, except when we go to a football game, we don't really behave as huge flocks, but are there sort of social behaviors, maybe obsessions or so forth, that human beings also can act as murmurations? Or am I wrong?
The point about the reason of murmuration is that each bird is going to imitate the birds nearby, because he has to avoid collision and so on. And therefore, there is many things in society where people try to imitate other human beings, try to imitate other human beings. For example, you can think of fashion. But also there's one particular case that we have studied, and is the distribution of baby names in the United States. Now, you see that you have, in certain moments, you have a certain fashion. For example, in the 60s, Jennifer was a very common name. Nowadays, I don't know what may be a very common name, maybe Isabella or something like that. And now what you can see, if we look to the distribution names in the United States, you see there are some states which have nearly the same distribution name of other states, and other states that have different things. And now what we did, we analyzed numerically these distribution names, because we have the recording of the names that were given to baby in the last century and something. And, for example, the things that discovered that, for example, in 1 century ago, the great division was the northern country and the southern one that were quite in a different way. And now what happens essentially after the thing changed in the 70s, and now the East Coast and the West Coast go very well together, and the center part of the United States goes in another direction. Something like, I would say, that the Democratic state use different names than the Republican one, roughly speaking. And now this is clearly that this in effect is clearly an effect that people hear probably different television channel, read a different newspaper, read different things, have different friends from in the United States. And also that is something that we published. And also we started to study if one can understand this type of waves, which are the state which they first start, and we found, but we had not finished our study, that there are some states which start 2-3 years before the other, some kind of fashion, and after the other state is systematically imitate. So this is something that can be done in many different subjects. The only point is to have the data, because if we would have the data of books sold in each state of the United States by Amazon, one could do this kind of study. But I fear that it would be very hard to have from Amazon this kind of data.
Yes, yeah, I agree. That's fascinating. Let's turn towards now the research that you did. Kind of buried the lead, as they say. I didn't mention that you won the Nobel Prize. Normally I do that in the intro, but I'll clean that up when I actually edit the video. But I want you to now drop in and start talking about your work on spin glasses. They're so fascinating. And the curiosity I think my audience would have is what inspired you to do that and invent this concept and collaborate to make this occur, and then possibly talk about some technological implications of them. So let's start with, what is glass, first of all? What is glass, and how does it have an applicability to spin? I mean, if you have, my glass starts to spin, I've got problems over here. So tell me, what is glass, first of all? And then what is a spin glass? Because I think the public understanding won't be as clear until you explain it rather than me.
Let's do the following. It's supposed that you take water. You cool the water and it becomes ice. And we know that this happens at a very precise temperature, 32 Fahrenheit. And so there is what happens here, in that case, a well-defined transition from something that you call liquid to something that you call solid. Now, suppose that you look to the wax of a candle. I mean, when you see that it goes down, you see that it's liquid, and after going out from the fire, it becomes more and more solid, but it's not really solid. It's something that you can push your finger in and deformate, and becoming cooler and cooler, become more and more rigid. Now, in this case, you don't have a real phase transition. You have a situation in which you have a liquid that at a certain moment becomes so rigid that you cannot really push it. And you have many other type of liquid of this type, like think of honey. Honey is liquid, but you usually don't do, but if you put in a fridge, it becomes really solid. So you have a lot of things, and real glasses, the window glass, belong to this category. And in Venice, you can see how people work with glasses when they are very hot. Now, spin glasses is some kind of material which have some glass properties. They behave with some respect as glasses, but they are done with spins. But if you ask me why I was interested, I became interested at the moment in which I did not know anything about spin glass. The only thing that I know that was a mathematical difficult problem, in the sense that somebody had tried to give a solution, but the solution was factually wrong, was inconsistent. And now, so I started to study how to solve the mathematical problem. And at the end of 1 year, I found the solution of computing the quantities that were needed to compute it. And for all that period, I was not at all interested to what spin glass were, to which was the possible experimental realization. I mean, if you want, the whole physics connected to spin glass was not interested to me. It was just a problem that I want to solve because maybe I want to show that I am good in solving problems, but not particularly interested to it. And at that moment, I left the problem. And after a few years, 3-4 years, we started by speaking with people to understand better the meaning of the solution. We started to have a new interest in the problem. We started to looking better and realized that the problem was connected to complex system. But it was a discovery that was done by analyzing further the problem a few years after that was done. And that was due also to the fact that other people were looking to the problem, and therefore I also found that there were interesting things to be understood, and I started to look again, and after looking again in details, one started that was connected to complex system.
And a spin glass itself is embedding magnetic or metallic particles inside of a glass, as I understand it. Are there any technological applications, resistors, transistors, quantum computers? Are there any technological spin-offs from these magical devices?
No, as far as I know, spin glass have no one has found a real application of spin glass. Someone was thinking maybe to have application as a memory, but was too complex to be done. No, what was had a lot of technological spin-off was a theory that was behind the spin glasses, because the theory that was behind the spin glass was not so different from the theory that Hopfield wrote down for the first modern type of neural network. And the spin glass and the theory of spin glasses was fundamental in the work that was done by other people, by the Israeli group led by Amit, to have a deep understanding of the Hopfield model of a neural network. And this made a strong push towards the understanding of neural network. Many people started to study analytically neural network because using the theory, modification, the theory, the type, for example, people were able to compute using this kind of theory, which was the maximum amount of things that a Hopfield network would be able to memorize. And in this kind of wave of interest for neural network, in the 90s, people started to propose what the deep network, which now are the deep networks, the deep neural network are now at the basis of modern artificial intelligence. Let's summarize that the interest in spin glass in the 80s have also a deep influence of the beginning of neural network, and this neural network are now artificial intelligences these days.
So my first book is called Losing the Nobel Prize. And it's about the story of how I came to invent an experiment that was looking for cosmic inflation and trying to understand the origin of the Big Bang via the imprint on the cosmic microwave background radiation, and how if we had been proven correct, then if the experiment had been confirmed, then somebody would have won the Nobel Prize. Maybe not me, but everybody agreed that this was the case. And in fact, we got a lot of attention. And then, spoiler alert, we did not win the Nobel Prize. And that's the name of the title. But a lot of people criticized me and they said, well, you can't lose the Nobel Prize because you don't really have it until you lose it. And I said, that doesn't make any sense. You can't lose a football game because you didn't win the football game. But it actually occurs to me that you did lose a Nobel Prize in a certain sense back, and you describe this in the book, to Kenneth Wilson. Can you talk a little bit about what Kenneth Wilson did, what you almost did as well? Can you talk about your actual losing the Nobel Prize before you actually won it?
There were two moments when I was very, very young. I was 25, that I lose in some sense the Nobel Prize. The first one was that I was interested to the same problem that Ken Wilson was interested to understand the renormalization, to understand not the renormalization group, because the renormalization group was the idea of Wilson, but to understand second order phase transition. But in this case, there was no match, because Ken had so many ideas, and he was working on the problem in the last 10 years. And so it's clear that I could not really match him starting in 1 or 2 years' time. So he had, just at the moment where I arrived to start to think about the problem, he came out with a solution. So this was really no match. The things on which we were quite near was the problem point of view of asymptotic freedom. Asymptotic freedom, which was a wonderful idea that got the Nobel Prize by Gross, Wilczek, Pulitzer in 2002 or 2004. I never remember.
Yeah, 2004. Yeah, Frank Wilczek has been on he's been a guest on the podcast.
Well, Gross, Wilczek, and Pulitzer got the Nobel Prize in 2004 for asymptotic freedom. But at that moment, I was really interested in this type of problems. And I knew that the same computation of Pulitzer, Gross, Wilczek was done by Toast, that was left unpublished. But Toast had not tried to apply this type of computation to real physics, which was the opposite of Gross-Wilczek. They discussed the quantum chromodynamics. So the things, I remember that I was in CERN with Toft, and we start to discuss how can one construct a model of physics in order to use his discovery. Now, we have only discussed half an hour because I was interested mainly to other problems connected to phase transition. Who also was interested in quantized gravity. And just the right solution, that was a model that was proposed by Gell-Mann 2 years ago, that I knew very well. I did not like the model in reality, but I knew the model very well. It came not to my mind the idea of applying to that model. Now, if I get the idea, or if someone would be present in the discussion and would just say, but what about the Gell-Mann model? It's clearly that all this, we could write a very similar paper to those people who got the Nobel Prize in 2 days, because all the computations were done, and it was easy for me to spell all possible applications. But the idea did not come to our mind. I was the expert on physical application. Toast was more interested to pure theory. So the fault was mine, certainly not of Gerard. But anyhow, we get something that in this case I was quite near a few centimeters away and the things escaped. Also, maybe it could be a mess because as far as probably also the other people in the United States would arrive at the same moment, would have 5 people with the same discovery, and which would make a cauchemar for the Nobel Prize committee. But I really do not know what would happen.
Well, my second book, thankfully, is not as obsessed with the Nobel Prize being lost, but it's about how to win one, potentially. So this is my second book. It's called Think Like a Nobel Prize Winner. And it's all about how you can collaborate and work with people to make the world more understandable. So I want to ask you about collaboration and how you view collaboration. Is it possible for scientists to work in isolation and not be involved with, say, experimental results if you're a theoretical physicist, or if you're a experimental physicist to not understand the theory? Is it possible to do things by yourself nowadays, or is it only possible with the help of collaborators?
Well, I think that it's really very, very difficult to do things to have a one-man work. Of course, sometimes we do have, but this is just an isolated spot, I would say, because in order to show the importance of this isolated work, you need the work of many other people. So this type of collaboration is very important. I mean, thankfully, I am very fond of collaborating with people. When I was 70 years old, people had just done a poster with all the names of people I have collaborated with, and there were 317 people. 2 years ago, or 1 year ago, maybe people did an update version of the poster with 360. So I am pretty sure that I'm supposed to go more than 400 of different collaborators. Sometimes our collaborators are only in one work. Sometimes our collaborators with which I have written 50 work together. But I think that collaboration is very important in these days, also because, and what is certainly important, to exchange your ideas with people. Because sometimes you have some idea, but they are very often the idea that people had are half-baked ideas. And in order to transform in really final things, you have to explain to other people, discuss with them, and so on, at least from my point of view. Of course, there may be other people that work in a different way. Einstein certainly thanks many discussions, at least in the first paper of relativity with Bessel and other friends and so on. The influence of Grossman was very important because for the general relativity, because for general relativity, it was needed a mathematics that Einstein did not know. Very few people knew at that time. Grossman, I really explained to him. On the other hand, Einstein won the Nobel Prize for the photoelectric effect, was really something that he did by himself, as far as I understand.
Yes, I think you're right. And what was so fascinating about this book, or many, many fascinating aspects of In a Flight of Starlings by today's guest, Nobel Laureate Giorgio Parisi, is that you kind of go through a checklist of what it's like to have an idea. And it's in a chapter called How Ideas Are Born. And I wonder if you could comment on it. You talk about these 4 steps, and we'll put them on the screen. There's a first preparatory step where the problem is studied, existing literature read, and first unsuccessful attempts are made. It's a period that can last between a week and a month because it ends when no progress occurs. Then there's a period of incubation, step 2, in which the problem is abandoned, at least consciously. 3, the incubation ends suddenly with a moment of illumination, which often occurs in an unrelated situation. And then 4, after the illumination provides the general way to tackle the problem, the solution must be formulated. Can you talk about your process, your work process? Do you follow this rigorously, or sometimes do you have ideas that can be made to fruition relatively quickly? Or do you really have to wait for these moments of inspiration, followed by maybe a fallow period when you're waiting, nothing much is happening, and you abandon it. How does that interplay work? Especially when you have collaborators. It's hard enough to have one idea of your own, but you have a collaborator. How do you get him or her to abandon it and work on it, et cetera? So can you talk about your idea generation process? How are ideas born?
Well, the point is the following, that it's not that I'm really following this program. I mean, it's not something that I do programmatically. Just thinking on a few cases in which I have some particularly good ideas, and also looking to something that's written in the literature, because other people describe the way that they got the idea. The famous case in which they tell. I mean, usually scientists do not tell people how they got the idea. They only present a final result, but not the way they get it. There are people that discuss Poincaré, there are the case of Keating, or there is something that is seen in the book of David Well after that he wrote My One. So many people describe the way that they get an idea, and this is something that is quite common. Of course, the fact that you need some months is something that, especially for very important and difficult ideas, but in certain cases, also for simple or for much simple things, is something that you need to. You work in a similar way. The only thing that the time scales is much shorter. For example, I remember sometimes that I started the morning to look to a new program. I realized there's a bug that does not work. The program code is wrong. And I spend the whole morning trying to understand what is wrong. And I am not able to find. But after that, I started driving for going to home at lunchtime. During driving, I understand what is wrong. I go home and I check that was exactly the same thing. So that's the fact that sometimes looking back, looking for a little far away is something that helps. Of course, when you have a collaborator, the things are somewhat easier if you are at this stage with collaborator, because you start to tell your collaborator your ideas. At the first time, they do not understand, but which are your ideas, so you have to formulate in a clear way that are understandable by them. I remember that for my 60 years, one student of mine gave me as a present a cactus, and a small cactus and saying, this is the way that the idea come out from the mind of Giorgio.
Today's episode centers on the math behind complex systems. So many people are passionate about science, but then find themselves intimidated and disengaged at the slightest hint of math. And this might discourage them from their own shot at a Nobel Prize. However, math becomes infinitely more intriguing when intertwined with mathematical notions, animations, and brilliantly planned lesson plans. And that's why I love Brilliant. It's a dynamic and engaging platform for learning mathematics, data science, and computer science interactively. I use it both on the website and on the fabulous Brilliant app, where you'll find a treasure trove of foundational advanced topics like group theory, artificial intelligence, networks, and the course I'm getting involved with, data analysis. It's here to help people fall in love with math and unlock new opportunities regardless of your proficiency. Brilliant tailors content to align with your learning needs, your pace, so you can progress at your own rate. Currently, I'm going through the lessons on the app for their quantitative financial modeling course. It's fantastic and opens up a new set of wrinkles in my brain, a side of mathematical analysis I've never even encountered before. It's a way of gamifying and making the learning process fun. You start the lesson and you're immediately drawn in with Brilliant's fantastic animations and customized pedagogical framework. It's the future of education. To try everything Brilliant has to offer for a full 30 days, visit brilliant.com/Dr. Brian Keating or click the link below. The first 200 of you will get 20% off Brilliant's annual premium subscription.
Well, I have to ask you about something controversial in your field of condensed matter physics. Although you've done so many things from high-energy particle physics to studying starlings, but recently there was a claim of the very first room temperature, ambient pressure, high-temperature superconductor. What did you make of the excitement, and what do you think is going to happen with high-temperature superconductivity? Do you think we'll have one, in the next few decades, or do you think it's almost impossible to imagine?
Well, first, all temperature superconductor will be very useful. First, all for doing toys for children, and also because there will be lots of gadgets which will consume much less electricity. So that will be very, very useful. And I feel that, I do not see any particular reasons for which we should not have high-temperature superconductors. Of course, it's clear that this is very difficult, also because we really do not fully understand why the actual superconductors that have reason that they are superconductor at the liquid oxygen, liquid air temperature, really the reason for which they are superconductors. There are some recent papers that claim they do understand, but I think that the space, the amount of different materials that can be constructed is so huge that especially at the moment in which when we'll have a good theory of high-temperature superconductors, I do not see any reason for which we could not have a room temperature superconductivity. Of course, I may be wrong, but I am quite confident that we can arrive to it.
I want to just ask about your work that you've been leading to really bring scientific funding in European governments to the high level. One of the topics in the book is how much value that science provides to a thriving society. And you talk about in the book this famous joke by Nobel Prize winner Richard Feynman, who said that science is like sex. Sometimes it produces useful results, but that's not why we do it. Can you talk about your movement that you've been heading called, and I'm going to butcher this, Salvemano la ricerca italiana? I hope I didn't butcher that. Can you talk about that? What drove you to start this for society?
The point was the following. In Italy, the research is not enough funded. The total amount of money that Italy is spending on research, private and state altogether, is a little more than 1% of the total gross income and total gross product. And this is something that, opposite to other countries like Germany, we stay near 2%. France is already 0.5% more than Italy. Korea is 4%. So 1 and something is really very bad for Italy. And this is really a problem because with this amount of spending, many brilliant Italians go abroad. They do not remain in Italy because there's not enough money to do reasonable research. They go in other countries, and this is something that makes Italy much poor. So what I've been started to push in the last 10 years, in the last 15 years, let's say, and maybe 20, more money for research. This is something which is that many Italian governments did not give more money. The reason is that although research is useful for increasing the national gross product in the long run, it's not in the time interval between one election and the other elections. So they are not really interested in doing that. So it's something that is really bad for Italy, and for example, the movement Salviamo la ricerca italiana, let's save Italian research, was a movement in which we started on a petition on change.org And we got 200,000 signatures asking to get more money to Italian research. And this took a certain amount of time to organize and to get this number of signatures. But this, I think, was helpful because it showed to the politicians that research was important. At that time, I think that this did not have any strong effect on the total amount of money that politicians were to going on. The only difference that made that before people or the politicians were not speaking about research. After the movement, they were saying that we give research a lot of money, but without increasing the amount of money. So they understood that it was important to say that they give money to the research.
Very good. And then the last thing that I wanted to bring up before I ask my final question, which is kind of a philosophical question, has to do with a quote that you have in the beginning of the book, which was really, it inspired me to write a tweet, which is, online. I said that, why do we need to have science communicators, people whose job it is professionally to communicate science? We don't have that with movie stars. We don't have that with football players. So why is it that science needs someone to make science more popular? And I got a lot of hatred online. People said, oh, that's stupid. Movie stars do get paid to go out and do it. And I said, well, yeah, that's proving my point. But scientists should be communicating more to the public, is my philosophy. And it's not a surprise that we don't get much funding, because a lot of times we do things to say that we can't really explain it to you as a lay person because you're not smart enough. Or we say that it's too hard for us as scientists to learn how to communicate properly. And I say that's nonsense. It's hard to learn the renormalization groove. So saying something is hard is not an excuse. So you said at the end of the preface, you say the following: I wanted to start to emphasize how difficult it is to understand the many phenomena that we observe almost daily, and convey that complexity is not about what happens in laboratories. It is what happens all around us. Our job as scientists is to illuminate for everyone the truths we discover. Can you say if you agree with this? I believe scientists have a moral obligation to communicate what they do in terms that people that fund us can understand. Do you agree with that, or do you disagree? And if so, how?
No, I fully agree with that. And I think the scientists have to understand that if they do not communicate with people what they are doing, the funds will stop eventually. So I think it is certainly a moral obligation, but also a long period need to communicate with people. Because science in these days, it costs a lot of money, and we can think of some kind of maybe not very efficient world in which technologies go on without science. And this is something that it may be difficult, but may be possible. And or you may have a situation in which both technology and science escape from small countries like Italy. This is also another possibility. So I think that it's extremely important. I fully agree. It's a moral obligation and also convenience for them to communicate. It's not easy. One has to study, because also communication with people should be done also in a fast way, because you have to get the attention of people. And therefore, it's not easy to get the attention of people. And also because scientists you normally are accustomed to use written words. And that this is not the way, and also to speak with people that are interested, like scientists. Now, the real problem for scientists to communicate is to get the attention of other people at the moment that they start to communicate, and that is the thing that make things different, because other people get immediate way, just looking to them in the face, you are interested in what they are doing, but not scientists.
Giorgio, that was beautiful. I really appreciate your time. And there's one last question before I'll let you return to have a buonasera. And that's the question I like to ask my guests, and ask them to give themselves advice when they were 20 years old to 25 years old. And it's based on the name of this podcast. So this podcast is based on Sir Arthur C. Clarke's third law, which states the only way of discovering the limits of the possible is to venture a little way past them into the impossible. So I want to ask you a question, Giorgio, for your former self at age 25. What advice would you give him to have the courage to do as you've done, to go into the impossible? What piece of advice, if you have 30 seconds with 25-year-old Giorgio, what do you say to him?
This question was already asked to me, and after some thought, I said that I will not give any advice, because I've been very lucky in the choice of things to study in my trajectory, and to hear some seminar. I mean, I think that I had a lot of luck, and I think that any disturbance of the trajectory would be very likely to have a quite negative effect.
Well, that's very smart, because here we have The Simpsons, a very famous cartoon where Homer Simpson goes back in time and he steps on a bug and he goes, "Stupid bug, you go squish now." And then fast forward 60 million years later, and humanity is a servant of all these bugs. So Giorgio, I want to thank you so much for this wonderful book. For the inspiration to millions of people around the world. You made so many people happy when you won the Nobel Prize, but really for the work that you've done and this fabulous book. And I hope we can meet someday in person and have a cappuccino together.
You are welcome if you come to Rome to have a cappuccino here.
Thank you. Mille grazie.